Hello, and welcome to another day of the Internet Measurement Village. Today, we're really happy to have join us Zack Weinberg from ICLab, and he'll be telling us all about how they're measuring internet censorship. Thanks for joining us, Zack.
Hi, everyone. Thank you, Arturo. I'm Zack Weinberg, and I'm going to tell you about ICLab, which does global continuous monitoring for internet censorship. Here at the Measurement Village, we've already heard presentations from two other groups doing similar things, UNI and Censored Planet, and several other groups doing closely related stuff. So if you haven't seen those presentations, I encourage you to go back and watch the recordings of those after I'm finished. ICLab is an academic project hosted at the University of Massachusetts Amherst, where I'm a postdoc. And right now, it's a part-time effort by me and the 7 other people you see on this slide. And we're spread over the 5 institutions whose logos are at the bottom. Our code is open source, our data is publicly available, and we're always looking for more help. Later in the talk, I'll mention some different ways people can get involved. You can contact us via our website, iclab.org, or by email, info@iclab.org. Now, since this is the 3rd talk at this village from a group doing global continuous monitoring for internet censorship, I thought I would start with a quick summary of how we're different. Like UNI and Censored Planet, ICLab probes for network interference continuously and worldwide. Unlike them, their focus is on collecting as broadly as possible. So some of the figures on this slide are out of date. I understand UNI has more countries now, but their goals are primarily to get as many vantage points as possible, and UNI does that with volunteers, and Censored Planet does that with open access servers. ICLab, on the other hand, we concentrate on capturing as much detail as possible, which means that we can only run a limited number of vantage points. We're currently focusing on website accessibility. Each time we run a test, we test all of the Alexa Top 500, all of the Citizen Lab's global list of sensitive websites, and all of the Citizen Lab's country-specific sensitive list for the country the vantage point is in. If you're wondering more about these lists, by the way, I believe there's another talk that's all about that. And we capture packet traces and we mimic browser behavior as closely as we can manage, so that we understand in detail what happens on the network level and on the application level when a website gets censored. Now, this does mean that we're accumulating a great deal of data. It's an average of 23 megabytes of data every time one vantage point runs a test cycle. So storage capacity has been a problem for us, and so has bandwidth consumption by the vantage point. And to collect packet traces, you need privileged access to the vantage point. I believe this is not actually possible from a mobile app unless the phone is jailbroken. So what we currently do is we rely on commercial VPN servers. That gets us the network access we need, and it avoids the practical and ethical problems with using volunteer work. But it means that we can only reach about 60 countries, and there are other problems. I wrote a whole paper about how commercial VPNs have this bad habit of lying about their physical locations of their servers. So what do we get out of all this detail? That's the rest of the talk. So just to give a brief overview of what I'm going to talk about, first I'm going to give a little background on what I mean by internet censorship and how it's done. And then I'm going to talk about 3 different symptoms of censorship that ICLab can detect: blocked pages, DNS inconsistencies, and packet forgeries. For each one, I'll talk about how our detailed measurements let us develop precise rules for distinguishing genuine cases of censorship from other phenomena that can show the same symptoms: ordinary network outages, sites refusing service to VPN clients, geo-targeted DNS responses, ad injection, and a few others. I want to point out that we needed all this technical detail to work out the rules that we use. but many of those rules could be implemented by other groups that can't collect the same detail. So if you work on UNI or Censored Planet or some other monitoring project, I'd like to encourage you to think of us as your methodology workshop. Is there something you've noticed but you don't have enough detail to analyze? Do you have cases where you think censorship is probably happening but you can't prove it? Come talk to us. We might be able to help. And after I talk about these symptoms and how we analyze them, I will show some case studies of specific things we found. And finally, I'll share a few ways everyone can look at our code and data and use them for your own analysis if you're interested. So, what do we mean by internet censorship? There's several different kinds nowadays, but what ICLab specifically studies is interference with network traffic in order to restrict access to specific types of content. This can happen at a local network or at the level of ISPs and NSPs or up in the backbone of the internet itself. And at all levels, it could be directed by national governments and motivated by politics. It isn't always, but it could be. And that's what we're most interested in discovering. Back in the early days of the internet, people would joke that the internet would interpret censorship as damage and route around it. But the truth is that content filters started being deployed around 1996. Which is almost immediately after the net was opened up to the general public and stopped being just this academic thing. And China's notorious Great Firewall, which is probably the most famous and most well-studied national censorship of the internet, that dates to 1997 and is constantly being improved. Nowadays, a solid majority of people who have access in the first place, by the way, that's still only about half of the planet's population, solid majority are subject to some level of censorship. On the right of this slide, I have Freedom House's assessment of 65 countries worldwide for how aggressively those countries restrict access to the net, scaled by the population of internet users in those countries. So you can see that maybe even not a third of people can get unrestricted access. Right now, ICLab focuses on detecting censorship of the web. We want to expand to more different protocols in the future, but right now it's all web. Now, in general, when you, an end user, try to access a censored website, what you might see one of two things. You might see what we call an overt block page, like the one on the left, which was written by the South Korean government's Communications Standards Commission. And the text says explicitly that you are forbidden to access a particular website under government authority because of the content of that page. And it gives you contact information if you want to dispute the classification. But the other thing you might see is a completely generic error message, like the one on the right. The browser is saying that it tried to connect to the site and it couldn't. There's no detail. There's no assertion of authority. There's no contact information. It could be that this site is just broken right now. On the other hand, it could be what we call covert censorship. And in the case studies later, I'm going to talk about a case where it was proven that a government was using overt censorship for material that was openly illegal in that country and covert censorship for material that was supposed to be allowed. Now, when either of these types of censorship happens, what ICLab records is what happens at the network level. So to understand what happens at the network level, I'm going to first quickly recap how a normal, non-censored, unencrypted access to our website works. So on this slide, we have our old friends Alice and Bob. Alice is running a health information website. That's her on the right. And Bob has some questions that he's a little too embarrassed to ask someone about in person. So he loads up Alice's website. Bob's computer first does a DNS lookup to turn the name of Alice's website into the IP address of its server. That's that first exchange. The query goes out over the network and the IP address comes back. Then it makes a TCP connection to the server. So it sends out what's called a SYN packet and it gets back a SYN ACK. And now the computers are ready to talk to each other with HTTP. Bob's computer sends a GET message naming the page that Bob wants to read, and Alice's server sends back the HTML, which gets rendered, and Bob sees the page. But Mallory, our old nemesis who is engaging in censorship today, can interfere at any point in this sequence. The man in the middle can sees the DNS request go out, sees the name of Alice's website, and can respond to that with a false response that says there is no such website, or the address for this website is actually a computer that Mallory controls. Or they can send a TCP reset packet to disrupt the handshake, based perhaps on the IP address being one that Mallory doesn't like. Or they can send an HTTP redirection that supersedes the text of the actual page. And there's several other possibilities. Mallory can't usually stop Alice's packets from coming through to Bob because that's impractical for a router running at backbone speeds. But as long as Mallory's packets arrive before Alice's packets do, the network stack on Bob's laptop will ignore Alice's packets just because Mallory's packets got there first. And sometimes Mallory will send disruptive packets in Alice's direction as well so that it will stop. Some of these tricks produce overt block pages, and some of them produce covert censorship. They just look like ordinary network errors. And I'm going to be going into detail about how these all work and what happens. So let's talk about the symptoms that are visible to software running on the client: block pages, DNS inconsistencies, and packet forgeries. So you saw a block page already, and here's a couple more. They're usually pretty easy for a human to recognize. And once you know you're looking at a block page, you can write a regular expression and make computers detect it in the future. That's how Uni detects block pages, and that's how we detect block pages too. There's no "this is a block page" bit somewhere in the TCP flags that we can see in our packet traces. It's all about the HTML text of the response. The challenge when you're working with block pages is how you discover them. Suppose you have a regular expression that detects the example block page on the left, which comes from an ISP in India. It might or might not also detect the very similar text on the right, which comes from a different ISP in India. They're obviously the same to a human, but they're not obviously the same to computers. Computers don't do obvious. You can't make a human read through all the HTTP responses you've collected to find the block pages that your regular expressions missed, because that would take far too long and they'd get bored and they'd stop paying attention and they'd miss stuff. And it gets worse. Here's some more block pages. Gosh, those look like ordinary HTTP error messages, don't they? It just says error 403, access denied, or 404, that's an error. File or directory not found. You see this all the time when you go to a web page that doesn't exist anymore. How do we know that these are not block pages? I do know that these are block pages, and in a couple slides, you'll see how. And here's one more. This is not a block page. It's the site, Craigslist, refusing to provide service to our IP address. This is not the government-sponsored censorship that we're interested in monitoring. But to a human, it looks a lot more like a block page than these generic error messages do. So when we're writing regular expressions, we need to not write one that catches this one. So how do we do it? Well, first off, here's how we know the generic errors are block pages. Because here's all on the left, here's all those texts I showed you minus the Craigslist one, and on the right, they were all using the exact same HTML template, which means it's the same software in use by all these different ISPs in India, and they just changed the text and left the structure of the page alone. And here is how we discovered that. We used two different types of unsupervised clustering. We can either pull out all the text and flatten the white space and then use a thing called locality-sensitive hashing to find texts that differ in only a few words. And there's an example of that on the left, where I think this was Iran, was faking parked domain messages for web pages they didn't like. And so the text is almost the same in each case, and locality-sensitive hashing puts them all in the same bucket. And then we we can see that. Or what we did to discover the HTML structure on the previous slide is we pulled out the HTML, threw away the text, we counted the tags, and that gave us this frequency vector, and we cluster those with k-means or any other unsupervised clustering algorithm you like. So now we have a bunch of clusters, and we still have to go through the clusters by hand and write new regular expressions, but it's so much less work. And we can make it even easier because here's a trick for distinguishing clusters that are block pages from clusters that aren't. So on the left, this is a real block page. It's an HTML fragment that redirects the browser from a censored web page to the Korean Communication Standards Commission's block page that you saw earlier. We received that fragment from 400 different URLs, but only in one country, namely South Korea. On the right, it's almost the same fragment, but it's doing something completely different. It's redirecting from a former small pornography site to the large tube site that bought it out. And we got this fragment on 70 different URLs, but we see them in 50 different countries. And this is what we call the URL to country ratio. If we see the same cluster only in one country, it's far more likely to be censorship. And so we sort the clusters from the largest to the smallest URL to country ratio, and that reliably puts the genuine block pages at the top of the list. And so using these techniques, we were able to discover about 50 new block pages, clusters, types of block pages that everyone was missing, and we wrote new regular expressions for them, and now everybody can detect them. And we can just keep doing this. Now, but sometimes you don't get a block page. Sometimes what you get is one of those covert error messages. And now we would like to go down to the network level and try to figure out what's going on. We get a no such host error message. Well, is that censorship, or is that a perfectly ordinary, this site no longer exists? And when you get a no such host error message, that's the domain name system, DNS, telling you that. So let's look at how we analyze what the DNS is doing and find inconsistencies. ICLab sends every DNS request twice, once from what we call the field node, which is in the country where we're looking for the censorship, and once from the control node, which is on a network in the United States or the Netherlands or Japan. There's 3 of them that we know doesn't get any censorship at all. We use whichever one is physically closest to the country where we're doing the field measurement. So we send the same DNS request to these 2 different ISPs DNS servers, and we get back 2 responses, and then we compare them. And on this slide, I'm going to take you through all the different possibilities. So the simplest possibility is that we get the exact same response in both places. That means that there is no censorship happening at the DNS level. There could still be censorship happening at a different point in the network exchange, but it's not happening in the DNS. But there's a bunch of perfectly innocuous reasons why you might get 2 different responses. So for instance, if we get 2 different IP addresses back, but they belong to the same network, same autonomous system, then that's still not censorship. That's what's called load balancing, where the incoming requests are getting split among several different servers, and they're all on the same network, so they're run by the same organization, so they're probably all serving the same website. This is really common with big websites. Another thing that happens with even bigger websites is we get 2 different IP addresses. They're both globally accessible, but they're in 2 different networks. And then we look at the IP address to country ratio, because what we could be looking at here is a global content distribution network that has servers all over the world. And so they have to buy them from different networks. But they're still all serving the same web page. And we can tell when we see, oh, that's this, all of these websites are coming from this one server when we access them from Southeast Asia, but the same set of websites are coming from this different server when we access them from Western Europe. But this third set of servers, when we access them from, I don't know, South Africa, it's probably a CDN. And on the other hand, if there's a whole bunch of websites that all get sent to the same address, but only in one country, that's probably a censorship happening. It's the same idea as the URL to country ratio I talked about earlier. And then there's some other possibilities where it's clearly censorship and we don't have to do this. We don't have to dig into it further. If we got a valid IP address from the control node, but we got a no such domain error message in the field, that's censorship. If we got a valid IP address from the control node, but we got a non-routable IP address like network 10, which is private use. And finally, the trickiest case, and the only case where we actually need to look at packet traces to notice what's going on, is when we get 2 or more responses to the same query happening in the field. This is a violation of the DNS protocol. It's not supposed to send back, a DNS server is not supposed to send back 2 responses with different contents to a single query. So when this happens, we know that one of those responses came from the real web server's DNS, and the other one came from a sensor that's operating by packet injection instead of by controlling the DNS server. And I should say that we don't know which one is true. We have to then contact both servers and see what we get. And a similar idea is when we look for TCP forgeries. And it's the same concept, but there's more possibilities. And so this slide is even more of a mess. We send, again, 2 GET requests from the control node and the field node. We get back 2 responses. In principle, those should be coming from the same web server, but maybe one of them is getting censored. And so if we see the same HTTP response, it's not. If we get different HTTP responses, it's still probably not censorship. And the reason for that is very often, if you access the same website from different places in the world, especially the really big websites, you'll get different stuff because they're doing what's called geo-targeting, where they're like, okay, you're coming in from Thailand, you probably want to see the webpage in Thai. Or we're going to serve you ads for companies that you can actually buy products from, or stuff like that. And at the same time, sometimes specific websites don't want to do business with anyone in specific countries, and so they just refuse service, and that's arguably censorship, but it's not the government censorship we care about, again. So we don't count that as censorship. As long as we don't see a packet collision in the packet trace. So packet collision is when you get 2 TCP packets with the same sequence number and different contents. Again, this is a protocol violation. It's not supposed to happen. But sometimes it happens and it's still not censorship. Sometimes we get 2 data packets and neither of them is a block page. And I thought, wow, that's weird. I looked at them. Turns out it's 2-bit errors. The packet checksum that finds out if the packet has been corrupted in transit can only detect single-bit errors. So if 2 bits are corrupted in transit and it's just right, then it'll come through to the higher layer and it won't get thrown out by the network stack, and we'll see this packet collision. But it's not censorship. And another case where it's not censorship is when we get a network error in both places. That's just a site outage. Perfectly ordinary, happens all the time. But here's some cases where it's more fishy. If we get a network error from the control node and we get a different network error from the field node, that's fishy. And the most common case where this happens is that a site is censored somewhere, but that site no longer exists, but it's still getting censored. So you try to load the domain name. The example I know about off the top of my head is this Blogspot blog that for a long time was talking about minority rights in Morocco. And then it got taken down, and for a while it was a park domain, and for a while it was a just no such domain at all. And if you go to it now, it's spam. But all this time, the government of Morocco has been blocking access to that website. They don't care what it's actually got. They didn't go back and notice, oh, wait, that blog no longer exists. So if you access the site from Morocco, you get a block page. Similar things happen all over the world. If you get a HTTP response in the control node, but you get a network error during the TCP handshake in the field, that's also probably censorship. That's probably the censor is sending a reset packet before the server, the real server could send any data, before the client could even send the GET. But we can't prove that yet. We have some ideas, but we're not there yet. And then cases where it is censorship are things like we see a packet collision and one of the packets has a block page in it. Or we see a packet collision and one of the packets has data and the other packet is a reset that disrupts the connection. And the wackiest case is when we get a network error at the control node and we get an HTTP response in the field. And again, this is the site no longer exists, but it's still being censored. So these heuristics, some of them do require that you have the packet trace so you can see the collisions, but I think that at least some of them could be adopted by other groups to improve their ability to detect covert censorship. So enough nitty technical detail. Now I'm going to show you some case studies of interesting things we have discovered. And finally, I'll talk a little bit about where you can find our code and data and how you can use it to do your own research. So case study number one is Yemen. Yemen has been having a civil war for the past 5 years now, I think. There's two groups, both claim to be the legitimate government. They're blowing each other up as we speak. It's really ugly. But even before there was a civil war, there was overt censorship known to happen. And that censorship focused on content forbidden by Islamic law, sites, gambling websites, sites that wanted to sell you alcohol, things like that. And it was overt. You got an explicit error message telling you that this is forbidden according to the law of Yemen. That increased in its thoroughness. They went after more websites in early 2015, right at the start of the Civil War. But at the same time, there were a bunch of other sites that started producing this generic 404 not found message. And all of those sites were news sites and political advocacy sites that were critical of the de facto Houthi government. And so ICLab, in collaboration with some people at the University of Toronto, we collected a bunch of packet traces, and we were able to prove by analyzing the IP ID and time to live fields in the packet headers, we were able to prove that this generic message was being injected by the same host that was injecting the overt block page. And so it was still censorship, but it was covert censorship instead of overt censorship. If you want to read more about that, there's a link at the bottom of this slide. Case study number two, Iran. Iran's government is also very big on censoring the internet, especially restricting access to foreign websites. And not just foreign news, but like foreign businesses. They want you to use Iranian businesses instead. But at the same time, the United States government often discourages United States corporations from doing business with Iranian citizens on various levels of like how much trouble will you get in if you do this. And so if a website that's run by a US corporation is inaccessible in Iran, there's a question, is that Iran's government? Or is that the United States government that's behind that? And again, by analyzing the packet headers, same packet headers, the IP ID and the time to live, we can tell whether the error message saying you can't use this website is coming from the actual server for the website, or it was injected by a router close to the client. And so we went through a bunch of websites. These are all really big multinational services. And some of them are being blocked at the level of the local ISP, and some of them are being blocked by the server. So in this case, it looks like Google is taking the US sanctions a little more seriously than Netflix is. And final case study, this is something we discovered that isn't censorship. This is another example of a cluster of HTML fragments that we saw in thousands of URLs only in one country. So our clustering algorithm threw it up as, we think this is a block page, but it's not a block page. It renders as a blank screen for 2 seconds. And then that topmost line of HTML that says meta refresh, that sends you to the page you originally wanted to visit. But in those 2 seconds, the rest of the code that you see runs. It sends some information about your browser off to a server whose IP address I deleted. And then that server sends back some more code that records and transmits even more information about you, along with the name of the page you meant to visit. So this is doing surveillance. It's probably for ad targeting, but we have no way of knowing for sure. This kind of thing is really surprisingly common, and it's not always surveillance. It could be cryptocurrency miners. It could be other forms of malware. This is the #1 reason why if you run a website, you should take it HTTPS only, make it all encrypted. Once that happens, this can't happen. So those are my case studies. And now I just want to, in the time I have left, I just want to talk a little bit about how you can use our code and data for your own research. All our code is open source and available on our GitHub account, which is github.com/ICLab. If you're having trouble finding something in there, contact us. It's academic code. It was written by graduate students. We are not always the best at software engineering for the long term. We will help you. If you want the raw data, you need to contact us because there's 30 terabytes of it. And we will probably need to give you access to our computers so that you can crunch it directly. Semi-processed data can be downloaded from the Internet Archive. And as soon as our sysadmin gets back from vacation, we're going to put an interactive data explorer on our website. And just as a teaser, I'm going to close out this talk with a few screenshots of that data explorer. It starts off by showing you all the countries where we observe censorship, and then you can drill down to a particular country. I'm picking on Brazil because we have a lot of measurements for Brazil, not because it does a whole lot of censorship in particular. And so it tells you like how many URLs we have ever tested in this country, how many measurements we've done, and how many URLs are observed to be censored. And then you can click through to a list of every single measurement, and it will tell you for each measurement what changed. So in this particular measurement, these 6 URLs got censored that weren't before. And this is just the beginning. We want to set up an API. We want to set up all sorts of different ways you can slice and dice our data. If you have ideas for ways that would be useful, please get in touch. Thank you. I will now take questions.
Thank you very much, Zach, for that really interesting presentation. So we've received several questions from people that have been following this video live. I will remind you that you can leave your questions at the pad that you see on the screen below. You can also leave questions in the Uni Slack channel or on IRC or in the YouTube chat. So the first question we received comes from Hussain, and he asks, in Iran, a new behavior of the Iranian censorship system is observed, which is a simple 503 error. Did you encounter it?
So we have not been able to collect data from Iran for the past several years. So it is not, that specific error is not in our data set. A simple 503 error would show up, if we could observe it, we would pop up in the block page clustering that we do. I'm confident that we could detect that if we had a vantage point in Iran, which we don't, unfortunately.
Okay. We have another question coming from Kyang. The question is, China is known to use routable IPs to inject DNS responses. How do you detect that?
I am not sure exactly what you mean by using routable IP. Do you mean that the injected DNS response contains a routable IP address? Or do you mean that the injected response is coming from some particular IP address that can be discovered? If it's the first case, the answer is we discover it by IP to country ratio. We notice that a whole bunch of websites are all being mapped to the same IP address, but only in one country. In the second case, that's something we currently cannot do, because what we cannot do is send out what's called time to live limited queries. It's on our to-do list. And I think we go off into the technical weeds if I try to explain exactly what I mean by that. So get in touch if you want to talk about it.
Yeah, they actually followed up saying that the question was related to injected responses containing routable IPs. Okay. So as you mentioned,
we've observed that in several different countries. And a particularly amusing one is when they send back an IP address for Facebook for some completely unrelated website. And so I think what happens if that goes through is you get Facebook's 404 not found page.
Yeah. I remember seeing this as well. That's a pretty peculiar behavior. Mm-hmm. And yeah, I guess in relation to the URL to country ratio, I will just highlight that DCF from IRC mentions that URL to country ratio is a good idea. I definitely also second that. It's really interesting heuristic that you're using there. He then goes on to share a snippet of code that you can run dig targeting a server located inside of China to easily experience DNS packet injection no matter where you live.
So that actually brings up a specific thing. A bunch of people have studied censorship by sending requests from outside the country they're trying to study to servers inside. And we don't do that. We only ever go from inside the country to outside. And that is a deliberate design choice, because we have found that sometimes what happens in those two cases is not the same.
Yeah, for sure. That's a really good point. So we have another question coming from David F. And the question is, what factors do you consider when deciding what VPN providers or data centers to use?
So we look for VPN providers and data centers that are within our budget and that offer access to countries, first, that we don't currently have access to, and second, to networks within those countries that we don't currently have access to. And the big catch, unfortunately, is that very often the VPN providers will say they have servers in all over the world, but really they're concentrated in a limited number of data centers, and they've just falsified the geolocation database to make it look like they have servers all over the world. And I wrote this entire paper about this. It's called How to Catch When Proxies Lie. It was presented at IMC back in 2018. And if unfortunately that talk never got put online. They said they were going to, and they didn't. But the full paper is available from my personal website, which I'm going to type into the chat.
We can also put it maybe in the video description as well after, if people want to follow up on that.
Mm-hmm.
And I see Maria just put the paper in the paper link inside of the chat, so
okay.
you should also get it there. So yeah, I'll just read Nguyen mentions as a follow-up to question number 2, so that on the routable IPs in the DNS injected responses in China, that although the Great Firewall uses public IPs for DNS poisoning, there's a set of such IPs. We use the set of IPs to help us in differentiating forged DNS responses. In addition, the design of the Great Firewall poisons both incoming and outgoing DNS query packets. Last but not least, although the Great Firewall injects forged responses, they don't drop the actual DNS response, if any. So if a DNS query was sent from the inside to a outside DNS resolver, we can expect to see the actual response in the PCAP. So, which was, I guess, related also to what we were discussing before. I have a curiosity, I guess, in relation to you mentioned like one thing that struck me was you were going over the third case, which was about the surveillance injection, and it reminded me a lot of a thing that we saw when doing some research in Egypt, where we noticed that they were using they were injecting ads into block pages, but also snippets of code that were used to do like mining, like Bitcoin mining. I had not seen, though, this thing where it's like somehow, for surveillance as like a 2-second delay and then redirecting you. I was wondering if you could share more details on that, like if you can, maybe in which country it happened and why you think that might have been the case.
So that happened for a short time on one specific ISP whose name I do not remember in South Korea. I believe they were one of the major South Korean mobile phone providers. And the reason I think it was ad targeting is that it was applied completely indiscriminately, no matter what URL you visited. And it only happened for a very short time. And so my guess, I don't really have any way of proving this, but my guess is that it was a pilot test of some sort of ad tracking and injection thing. And the 2-second delay got them so many complaints that they gave up on it. We did actually see some cryptocurrency miner injections in Brazil that were tracked to a known botnet. Infecting, I think, micro-tick routers.
Wow.
And that's something I'd like to do more with in the future, because it's possible that we could have detected that botnet earlier than anyone else if we had been analyzing our data sufficiently quickly. And so in the future, I would like to improve the efficiency of our data processing pipeline and everyone's data processing pipeline, so that we can catch stuff like this and report on it in real time. Also, the Egyptian like ads in block pages thing reminds me of a case study that I couldn't fit, where I believe this was South Korea again, we were seeing ISP level censorship injections stomping on backbone level censorship injections. So we have two different agencies trying to censor the same web page and tripping over each other.
Wow, that's really interesting, and it definitely sounds like a very annoying thing if when you're trying to access a website, you have a 2-second lag because they're trying to serve you some ads. It sounds like a really badly thought out.
I see in the chat that someone says that Arancel was displaying their logo on all HTTP sites, and I've actually seen that myself in the United States. A really sketchy cell phone provider was injecting their ads into everything.
Right.
I demanded my money back.
Yeah, that sounds horrible. Yeah.
Mhm.
And yeah, we definitely see more and more censors and ISPs using censorship as a way to make an easy buck as well, like of
Yeah,
block pages,
yeah,
including a bunch of ads and other ways of further monetizing on the censorship
yeah.
business.
It's important to keep in mind that the technology is completely value neutral. You can use the same technology to inject ads, to inject block pages, to block access to sites because you don't like their politics, because you don't like that they're selling alcohol, because they're doing copyright infringement. It's just a matter of what the filter list is.
Right. Yeah. Yeah, for sure. So we have another question that comes from David. Do you ever have trouble with using VPNs to get into a country that practices censorship, given that common VPN protocols are often targeted for blocking?
So oddly enough, this has not been a problem for us. We did observe a problem with China specifically, where if you transmitted enough encrypted data, I think that was over SSH protocol, which can be used for tunneling, they will disconnect you and not let you connect again for a period of like hours. But that was several years ago, and I haven't seen it happen again. My guess is that the commercial VPN providers will not deploy an actual server to a country where this is going to be an issue. And so it may well be happening in the countries we don't have access to for this exact reason.
Right.
Um,
Yeah, that's interesting. There's another question coming from David again, and he asks, "Do VPN providers ever mess with packets in weird ways? Like, do any of you, for example, secretly NAT you?"
oh yes, this is also something we have to weed out providers based on. The most obvious problem that we've encountered is that they just throw away ICMP time exceeded packets, which means you cannot do a trace route through them at all. Sometimes very often you're behind NAT. That is, especially in countries where IPv4 addresses are scarce. And that we actually don't find is a huge problem. It can be a problem if their NAT gets overloaded. And so we have to slow down the probe so that it doesn't start getting spurious failures. But we already have a bunch of code to deal with spurious failures. Those are the cases I can think of off the top of my head. But yeah, we try not to trust these outfits as much as we can.
Right.
Well, something I haven't seen, I should say, is ad or surveillance injection by the VPN provider, which is something we're on the lookout for, but so far it hasn't happened.
Because I guess the VPN providers you use are like you're paying for them in a way, or
yeah,
you also use free ones.
Sorry,
you also use free ones like open VPNs that are not that you don't have to pay for.
We currently do not use anything, and especially we don't use anything that's ad supported. Currently, I think there's 6 providers we use, and they're all paid.
Right.
So those are indeed less likely to have a problem.
Okay. So we have another question coming from Maria. She says, "I'm sorry if I missed this at the start of your presentation. How do you engage volunteers to run Sentinel?"
So right now we're not. Right now, any volunteer-operated devices are the very small number of volunteer-operated devices that we have right now are ones that were deployed several years ago, and we keep using them as long as they're up, but we're not deploying new ones right now, and this is almost entirely for operational reasons, because we are running on we're running on part-time people, and we don't really have the resources to reach out to volunteers and keep in touch with them. The volunteer operated devices that we do have, they are Raspberry Pi devices. They're very similar to RIPE Atlas measurement nodes, if you're familiar with those.
Yeah.
And we just had so many operational problems. Like, people would get them and they would plug them into their networks and they wouldn't work, and it wound up being too much of our very limited time to keep that going. It might be something we'd go back to in the future, but
yeah, we definitely had a very similar experience for the short time that we were also doing the Raspberry Pi shipment game, and it turned out to not really be easy to sustain that type of deployment case. So yeah, we also eventually ended up focusing more on mobile or desktop. So and Maria follows up. She also knows it well. She says, "We feel you." So another question comes from Ramakrishna. Are you planning to add support for measurements on more protocols? If so, which ones?
Yes, we are. The current top priorities are voice over IP, instant messaging, and VPN protocols. We're also talking with some people about doing bandwidth monitoring so that we can detect when the government is slowing down the internet for everyone, which is a thing that's apparently been happening more and more often. We're limited on coding people who have the ability to write the code, basically.
Interesting. I mean, I would say that especially about the instant messaging tests, if we should speak about that, because we've had a bit of experience in building them, and also some challenges that we have dealt with that maybe there's some potential for collaboration there.
Yes, definitely. Let's discuss that.
Yeah, and actually speaking about these protocols, I guess one thing that came to mind is you mentioned that one of the techniques that you have basically these three techniques that you go through. One is looking at like reset injections, DNS level inconsistencies, and also HTTP block pages, like injecting of block pages. I wonder if in recent times, with the web becoming more and more encrypted and more reliant on HTTPS, you have noticed somehow a trend or a difference in maybe that technique being used less and instead relying on more on the other ones.
So there's a subtle technical point here. When we detect a block page, it's always the case that one of the other things has also happened. And that's because in order to make that block page show up, the sensor has to have done one of the other two, has to have either tampered with the DNS or the TCP exchange in order to make the block page show up. So it's not that these are unrelated ways of causing censorship to happen. There is an exception, which is that they could be routing all traffic through an HTTP proxy, but this is extremely expensive and slow, and so mostly does not happen for larger countries. I believe it has been reported for Iran in the past, probably not anymore. The trend is indeed away from tampering with traffic after encryption starts happening. But even before the encryption starts happening, the name of the website goes over the wire in clear text several times. So the sensor has the opportunity to interject before the website becomes encrypted. And browsers have some security measures, like strict transport security prevents a website from being accessed as unencrypted. And so that would downgrade, the effect of that would actually be to turn an overt block page into a covert network error. Because they're trying to send an overt block page, but they can't because the browser is refusing to access the overt block page because it's unencrypted. And so you get this site is misconfigured, essentially error instead. Almost all of our testing right now is of plain HTTP. And again, we need to sit down and write the code to notice these HTTPS specific cases. The other thing we need to get a handle on, especially if we're going to do IM and stuff, is censorship within the application, where the protocol is not getting censored, but the client has some keyword blacklist in it. And that's something we currently can't really handle at all.
Interesting. Yeah, that's definitely a whole other dimension. But yeah, I guess I was curious about that because we've definitely started to see a trend in how, in a way, censors may not even care to like bother that much anymore, because if the site is has HTTPS and it has like HSTS or like high strict transport layer security headers being set, in the end, even if you do DNS injection and you serve a block page, the user most likely will never see it because they'll be stuck at the certificate error page.
Yeah.
So
yeah, very much so.
I mean, we haven't really looked at it systematically. I guess I was just.
So this is on our radar as something we need to look at systematically. And again, we'd be interested in seeing if we can share data sets and stuff.
Yeah, for sure. So we have a question that comes from Ma. And the question is, how much cost to purchase VPN servers annually? Looks like you have so many VPN nodes, which raises concerns about the financial feasibility to run your platform in many years.
VPN subscriptions is not the major cost, actually. The major cost is actually disk space. We are burning through disks at the rate of something a little less than a terabyte a month, and we cannot keep that up. We're doing some things about this, but it's an issue. The cost for VPN subscriptions is on the order of $50 US a month. So that the way these services work is you pay a monthly fee and you then have access to a whole bunch of servers. So it's not a per node cost, it's a per service cost. And so we're very selective about adding new services to the pool.
Okay. I see they're typing a follow-up question, and it's about, I guess, related to the costs associated to like storage space. So have you thought of putting your data on S3 or similar platforms that support academic projects, just like Uni has been doing? I guess they're referring to the Amazon Open Data program that gives you sort of free infinite S3 credits.
I haven't looked. The last time I looked at cloud storage, that wasn't an option, and S3 would be more expensive than just buying hard drives ourselves. That may have changed with this open data program. I will have to look into that.
Yeah, I guess the caveat there is that you need to make all the data entirely open.
So that there's a potential there for problems with the volunteer operated devices. Because that might have like information that reveals their location or something. But another reason, perhaps, to stick with the VPNs.
Yeah, there we go. Well, I think that's about the time that we had questions for. I would like to thank you so much again, Zack, for joining us today and presenting the work that you and all your colleagues have been doing at ICLab. I would also like to thank you and all your colleagues for the really important work that you're doing to advance the field of network measurement and helping us get a better understanding of how information controls and internet censorship occurs around the world. So thank you for that.
You're welcome. Thank you for listening, everyone.
I would also like to thank everybody from the internet that joined in today for the live stream, the people that maybe are listening to this in the future. I will also remind you that tomorrow you're in for a treat because we have not one, but two sessions covering two very interesting topics. The first one will be at 1400 UTC from Shames and Rodriguez from TunnelBear, and they'll be telling you about circumventing internet censorship with TunnelBear. The second one will be at 1700 UTC, and it will be from Kevin Bach from the Geneva Project, and it will be about how they're developing an evolving censorship evasion tool. So be sure to tune in tomorrow as well, and have a great day, evening, or, see you around. Ciao.